Almost every galaxy in the universe is running away from us. Their light arrives stretched, reddened, drained of energy by the endless expansion of space itself. Wherever we point our telescopes, in every direction, we see the same quiet retreat. The cosmos is emptying. Everything is drifting apart. But there is one exception, one faint smudge of light in the northern sky, a soft oval you can just barely see with your own eyes on a moonless night, that is doing the opposite. Its light is not stretched, it is compressed, squeezed toward the blue end of the spectrum. And that single detail changes everything. It means Andromeda is not leaving. Andromeda is coming. A galaxy of roughly 1 trillion stars, more than 150,000 light-years across, is falling toward us at about 110 kilometers every second. That is nearly 400,000 kilometers per hour. It has been falling for billions of years. It will keep falling for billions more. And when the two great spirals finally meet, neither will survive as it is tonight. But this is not a catastrophe, not in the way you might imagine. There will be no explosion, no shockwave of fire sweeping across the stars. What is coming is something far stranger and far more beautiful. A collision so slow, so silent, and so vast that any creature living through it would never feel a thing. Tonight, we watch two galaxies fall into each other, and we take our time. If you find peace in the quiet, enormous stories of the universe, consider subscribing to the channel. Let the slow gravity of the cosmos carry your mind somewhere calm as we drift through the deep together. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We are leaving Earth behind, not just Earth, but the whole solar system. The sun shrinks to a pinprick, then vanishes among the crowd. We rise upward, out of the flat, glowing disk of the Milky Way, until the spiral arms unfurl beneath us like slow smoke frozen in place. From here, you can see the shape of the place we call home. A barred spiral, 100,000 light-years wide, 400 billion stars turning patiently around a dark, heavy center. And then we turn and look outward into the void beyond. There is very little out here. 2.5 million light-years of almost perfect emptiness. A few wandering dwarf galaxies, thin threads of hydrogen too cold to shine, and ahead of us, growing slowly larger, a second spiral, tilted, enormous, glowing softly along its dusty lanes. This is Andromeda, also called Messier 31. And it is the nearest large galaxy to our own. Tonight, we will drift alongside it as it falls. We will learn how astronomers discovered it was moving toward us, how they measured a motion so small it took a century to detect. We will find out why almost no stars will actually strike each other, and what will happen instead. We will watch the tidal tales unwind. We will follow our own sun as gravity throws it somewhere new. We will listen for the two supermassive black holes spiraling toward each other in the dark. And we will stay long enough to see what is finally born from the wreckage. Settle in. Let your breathing slow. This story takes billions of years, and we have all the time in the world. Let us begin with Andromeda itself. It is old, older in some ways than our own galaxy. Its first stars ignited more than 10 billion years ago when the universe was still young and violent and crowded. Since then, it has grown by feeding, pulling in smaller galaxies, digesting them, folding their stars into its halo. Today, Andromeda is the largest galaxy in our neighborhood by size. Its glowing disk stretches roughly 150 to 200,000 light-years from edge to edge, noticeably wider than our own. It holds something close to 1 trillion stars, though that number is uncertain and has been revised many times. For decades, astronomers assumed Andromeda was far heavier than the Milky Way. More recent measurements suggest the two galaxies are closer to equals in total mass, roughly 1.5 trillion times the mass of our Sun each, once their invisible dark matter is included. That near equality matters enormously. When a large galaxy swallows a small one, the small one simply dissolves. The big spiral barely notices. But when two galaxies of similar mass meet, neither one wins. Both are torn apart. Both are rebuilt. What emerges is not the Milky Way with Andromeda inside it. What emerges is something entirely new. Andromeda also carries a dark heart. At its center sits a supermassive black hole of roughly 100 million solar masses, perhaps more. Compare that to the 4.3 million solar masses of Sagittarius A star, the black hole sleeping at the center of our own galaxy. Andromeda's is more than 20 times heavier. Remember these two objects. Long after the stars have settled, they will still have unfinished business with each other. Now, how do we know any of this? For most of human history, Andromeda was simply a smudge. Persian astronomers described it more than 1,000 years ago as a small cloud. Through early telescopes, it looked like a faint spiral of glowing mist, and astronomers argued bitterly about what it was. Some believed it was a nebula, a swirl of gas inside our own galaxy, a solar system in the middle of being born. Others believed it was something far more unsettling, an island universe, a separate galaxy unimaginably far away. The argument was settled by a single star. In 1923, working with the Great Telescope on Mount Wilson, Edwin Hubble photographed Andromeda and spotted a star that brightened and dimmed in a steady rhythm. It was a Cepheid variable, a type of star whose pulse rate reveals its true brightness. Compare true brightness to apparent brightness, and distance falls out of the arithmetic. Hubble made the calculation. The answer was staggering. That star was far beyond the edge of the Milky Way. He had crossed out the word nebula on his own photographic plate and written a new word above it, variable. That one correction quietly enlarged the universe by an unimaginable factor. The Milky Way was not everything. It was one island among countless others, scattered across a sea of darkness with no visible shore. We now measure Andromeda at about 2.5 million light-years away. The light entering your eye when you look at that faint oval left it long before our species existed. You are not seeing Andromeda. You are seeing a 2.5 million-year-old memory of it. But that's not all. Because a decade before Hubble measured the distance, another astronomer noticed something even stranger. His name was Vesto Slipher. In 1912, working at the Lowell Observatory in Arizona, he spread Andromeda's faint light into a spectrum and studied the dark absorption lines running through it. Those lines are fingerprints of chemical elements, and they sit at precise known wavelengths. If an object is moving away from you, its lines shift toward the red. If it is moving toward you, they shift toward the blue. Andromeda's lines were shifted blue, strongly blue. Slipher calculated that this faint smudge was approaching us at about 300 kilometers per second, the fastest motion anyone had ever measured for a celestial object. He did not yet know it was a separate galaxy. Nobody did. He had simply found a spectral oddity that made no sense. Today, we understand the number better. Once you correct for the Sun's own motion around the center of the Milky Way, Andromeda's true approach speed is roughly 110 kilometers per second, straight toward us. That sounds fast, but the distance is so absurd that speed becomes almost meaningless. At 110 kilometers per second, Andromeda closes the gap between us by only about 1 light-year every 3,000 years. It has 2.5 million light-years to cross. The fall has already been underway since long before Earth had oxygen in its air. And it will continue long after our Sun has died. Now, let's go deeper. Because knowing something is falling toward you is only half the picture. Imagine standing in an open field while someone throws a ball in your general direction. Knowing the ball is approaching tells you almost nothing. What you really need to know is the sideways motion. Will it strike you or sail harmlessly past your shoulder? For a galaxy, that sideways drift is called the transverse velocity, and it is brutally difficult to measure. A blue shift can be read from a single night's light, but sideways motion has to be seen. You have to watch a galaxy physically slide against the background sky. And Andromeda is so far away that its apparent movement is smaller than the width of a human hair viewed from across a city. Between 2002 and 2010, astronomers used the Hubble Space Telescope to photograph the same star fields inside Andromeda again and again over a span of years. They then compared those images with extraordinary precision, tracking the tiny drift of thousands of individual stars against distant background galaxies. In 2012, they announced the result. Andromeda's sideways motion was very small, almost zero, which meant the fall was very nearly straight in. A direct hit. Later, the European Gaia spacecraft mapped the motions of more than 1 billion stars with even greater accuracy and revised the picture slightly. The encounter now looks less like a head-on strike and more like a very close grazing pass. But the outcome barely changes. Once two galaxies pass that close, gravity does not let them go. And yet, there's more to this story, because Andromeda and the Milky Way are not alone out here. They belong to a small gravitational family called the Local Group. Roughly 80 known members sprawled across about 10 million light-years of space. Almost all of them are faint dwarf galaxies, shy little clusters of stars orbiting their larger neighbors. There are only 3 large members: Andromeda, the Milky Way, and a third, quieter spiral called Triangulum, Messier 33, about half our size and drifting near Andromeda like a smaller sibling. Everything else in the universe is moving away from us. Dark energy is stretching the space between distant galaxies faster and faster, pulling the cosmos apart. But within the Local Group, gravity has already won. These galaxies are bound to one another. They are close enough and heavy enough that the expansion of space cannot separate them. No matter how the universe grows, this small family stays together. That is why Andromeda approaches while everything else retreats. It is not defying cosmology. It is simply inside our gravitational island. And inside that island, the old rules still apply. Things fall. Triangulum will most likely join the collision too, drawn in by the same gravitational choreography, though its exact role remains uncertain. It may arrive early, it may be flung outward, it may fall in last, long after the main event has ended, adding one more river of stars to whatever is left behind. But what happens when we look closer at the space between us?
We picture galaxies as bright disks separated by absolute emptiness. That picture is wrong. Every large galaxy is wrapped in something enormous and invisible, a halo of dark matter, and a vast, tenuous atmosphere of hot gas called the circumgalactic medium. The Milky Way's dark matter halo extends far beyond its glowing disk, perhaps 1 million light-years in every direction. Andromeda's halo is at least as large. Recent observations using distant quasars as background lamps have traced Andromeda's gaseous halo outward for well over 1 million light-years. Do the arithmetic, and something quietly astonishing appears. 2.5 million light-years of separation. 2 halos, each reaching outward more than 1 million. They are already touching. The collision has, in a sense, already begun. Out in the deep dark between our galaxies, the outer envelopes of Andromeda and the Milky Way are already brushing against each other. Thin gas mingling with thin gas. Dark matter overlapping dark matter. The first faint pressure of an embrace that will take billions of years to close. Nothing visible marks this boundary. No light, no sound. If you were floating out there in the space between, astronaut, you would see nothing but 2 soft smudges of light, one ahead and one behind, and stars scattered across an otherwise empty sky. And yet, you would already be inside both galaxies at once. The journey continues. And it is worth remembering that neither of these galaxies is innocent. Both are cannibals. Both were assembled from the bodies of smaller galaxies they consumed long ago. When astronomers study the orbits of stars in the Milky Way's inner halo, they find an entire population moving the wrong way, on strange, stretched, chaotic paths that do not belong to our disk. These stars are the remains of a dwarf galaxy that fell into us around 10 billion years ago. Astronomers named it Gaia Enceladus. It was shredded, absorbed, and scattered. Its stars are still here, still orbiting, still carrying the memory of a galaxy that no longer exists. And the feeding never stopped. Right now, on the far side of the galactic center, the Sagittarius dwarf galaxy is being pulled apart. Long streams of its stars are wrapped around the Milky Way like ribbon unspooling from a torn package. It has passed through our disk several times already. Some models suggest those passes disturbed our gas clouds and triggered waves of new star formation, possibly including the burst that produced our own sun. Andromeda has an even more violent history. Its halo is thick with the debris of past meals. One study suggests Andromeda devoured a galaxy roughly the size of the Large Magellanic Cloud about 2 billion years ago, and that the small, dense companion we see today as Messier 32 may be the stripped, naked core of that victim. A galactic heart with all its outer body torn away.
Galaxies grow by eating other galaxies. What is coming is not an anomaly. It is simply the largest meal either of them has ever attempted. Now, let's go deeper into the question everyone asks first. When two galaxies collide, how many stars crash into each other? The answer is almost certainly none. To understand why, you have to feel the emptiness properly. Our Sun is a sphere about 1,400,000 kilometers across. The nearest other star, Proxima Centauri, sits roughly 40 trillion kilometers away. That is a gap nearly 30 million times wider than the Sun itself. Shrink it down. Imagine the Sun as a single grain of sand, small enough to rest on your fingertip. On that scale, the next grain of sand is about 45 kilometers away. Then another grain, another 45 kilometers beyond. Now scatter 400 billion grains of sand across a space the size of a continent. And then take a second continent of scattered sand and slide it slowly through the first. Not one grain touches another. The stars will simply pass through each other's territory like two clouds of smoke drifting together, interpenetrating without resistance. Orbits will bend. Constellations will dissolve and reform. But the odds of any two stars physically striking each other during the entire merger are so small that most simulations produce exactly 0 collisions. If there is anyone alive on any world during that time, astronaut, they will not be scorched or shattered. They will simply look up over hundreds of millions of years and slowly notice that the sky has changed. But if the stars pass harmlessly through each other, what actually collides? The gas. Galaxies are not only stars. They are also enormous clouds of hydrogen and dust, spread thin across the disk in vast, cold, dark structures. And gas behaves nothing like stars.
Stars are tiny points separated by unimaginable gaps. Gas clouds are hundreds of light years wide. When two galaxies pass through each other, their gas clouds cannot miss. They slam into each other at hundreds of kilometers per second. The gas compresses violently. It shocks. It heats. And compressed gas is exactly what stars are made from. Across both galaxies, in the same cosmic instant, cold clouds that had drifted quietly for billions of years suddenly collapse under their own weight. Star formation ignites everywhere at once. Astronomers call this a star burst. The rate of new star birth may rise by a factor of 10 or 100. Millions of brilliant blue stars flare into existence. The most massive of them burn furiously and die young, exploding as supernovae within just a few million years. Those explosions blast fresh energy back into the surrounding gas, carve out glowing cavities, and light the merging galaxies from within. For a few 100 million years, the merger will be the brightest object in this entire region of the universe. A slow, silent fireworks display of creation and destruction, unfolding over a span of time so long that no single moment of it would ever look dramatic. And this same burst carries the seed of the ending. Because every star born is gas removed from the reservoir, and that reservoir is finite. And yet, there's more to this story. So let us watch the choreography itself. The standard timeline, based on simulations by astronomers including Thomas Cox and Abraham Loeb, runs something like this. Around 4 to 4.5 billion years from now, the two galaxies make their first pass. They do not stop. They sweep past and through one another at enormous speed, and the gravitational shock deforms them both. Spiral arms unwind. The neat disks buckle and warp. Then something extraordinary happens. As the galaxies pull away from each other, gravity drags immense streamers of stars out behind them. These are tidal tails, graceful curving arcs hundreds of thousands of light years long, made entirely of stars pulled loose from their homes. Two great luminous ribbons unfurling into the void. But the galaxies do not escape. They have already given away too much energy. They slow, stop, turn, and fall back toward each other. Roughly 1 to 2 billion years after the first pass, they meet again. This second encounter is far more destructive than the first. The remaining structure collapses. Whatever is left of the spiral arms is erased. And then, over another billion years or so, the two cores spiral inward and finally settle into one another. The merger completes somewhere around 6 to 7 billion years from now. What remains is a single galaxy. Its stars no longer orbit in a flat, orderly disk. They swarm on long, randomly tilted orbits in an enormous, smooth, glowing ellipsoid. Astronomers have already given this future object a nickname, Milkomeda. Now, let's go deeper into why the galaxies cannot simply bounce apart. Two mechanisms conspire against them. The first is called dynamical friction. As Andromeda plows through the Milky Way's dark matter halo, its gravity pulls the surrounding dark matter toward it. But that matter arrives slightly late, gathering into a faint wake behind the moving galaxy. That wake has mass, and its gravity pulls backward on Andromeda, gently and relentlessly slowing it down. There is no fire and no friction in any ordinary sense, just gravity tugging quietly from behind. But over hundreds of millions of years, it steals orbital energy without pause. Every pass leaves both galaxies moving slower than before. This is why the second approach is shorter than the first, and the third shorter still, until the two cores have no energy left to separate. The second mechanism is called violent relaxation. During a merger, the gravitational field itself is changing rapidly. Stars are no longer orbiting a stable center. The center keeps moving. Under these shifting conditions, individual stars gain or lose energy almost at random, scrambling their orbits completely. The old, ordered, rotating disk is not destroyed by any impact. It is forgotten. Stars simply lose the memory of the neat circular paths they once followed and settle into a swarm of long, random orbits pointing every direction at once. That is why merging spirals produce ellipticals, not because something is smashed, but because the gravitational bookkeeping is erased and the stars have to start over. But what happens when we look up? For an observer on a world like ours, the merger would never be an event. It would be a slow change in scenery across hundreds of millions of years. Today, Andromeda is a faint oval visible to the naked eye only from truly dark places. It looks small. It is not. Its full extent already spans several times the width of the moon in our sky. We simply cannot see the faint outer regions. In about 2 billion years, it will be unmistakable. A glowing spiral hanging in the sky, brighter than any star, its shape clearly visible without any instrument at all. By 3.5 billion years, it fills a large portion of the sky. A vast, tilted disk of light, its dust lanes traced in silhouette, drowning out the constellations behind it. At around 4 billion years, the two galaxies begin to pass through each other. The sky becomes strange. Two overlapping rivers of stars cross at an angle. Enormous glowing clouds of newly forming stars burn in pink and blue along the shock fronts. There are no familiar constellations left. There is no Milky Way band arcing overhead because the disk that created that band has come apart. And then, over billions of years more, the chaos settles. The night sky slowly smooths into a soft, uniform glow, scattered evenly in all directions. Beautiful, calm, and utterly unlike anything any human being has ever seen. The journey continues, and now we follow one particular star, ours. Where does the sun go? In the simulations, most stars survive the merger without any drama. but they do not stay where they started. Our Sun currently orbits about 26,000 light-years from the galactic center, in a fairly quiet suburb of the disk. During the merger, that address will not hold. The Cox and Loeb simulations found that the most likely fate for the Sun is to be thrown outward. There is a substantial chance it ends up more than 100,000 light-years from the new center, far out in the sparse outer halo of Milkomeda, on a long, slow, looping orbit. There is also a smaller probability, a few percent, that the Sun is ejected entirely, flung out along a tidal tail, given just enough energy to escape the merged galaxy forever, and set adrift into intergalactic space. Imagine that sky, astronaut. A world drifting alone in the dark between galaxies. Almost no stars overhead, just an immense, silent glow behind you, growing slowly smaller across the eons. The loneliest possible view in the universe, and also, perhaps, the clearest. There is no way to know which path our Sun will take. These are statistical outcomes, not predictions. The Sun's fate depends on precisely where it happens to be in its orbit when the collision peaks. A detail no simulation can pin down billions of years in advance. And yet, there's more to this story, and it is a quiet, difficult truth. Whatever happens to the Sun during the merger, Earth will not be there to see it. Our Sun has been slowly brightening since it formed, and it continues to brighten by about 1% every 100 million years. In roughly 1 billion years, that added heat will be enough to push Earth past a threshold. Oceans will begin to evaporate in earnest. Water vapor is a powerful greenhouse gas, and the warming will feed itself. Our planet will most likely lose its oceans to space long before Andromeda ever fills the sky. In about 5 billion years, the Sun will exhaust the hydrogen in its core. It will swell into a red giant, expanding outward past the orbit of Mercury, past Venus, perhaps to the edge of Earth's orbit itself. Whether our planet is swallowed or merely scorched into a bare molten rock, the outcome for anything living is the same. So the timing is almost poetic. The merger with Andromeda peaks at roughly the same moment our Sun reaches the end of its life. Two endings arriving together after billions of years of separate, patient countdown. Nothing that remembers us will be watching. No human eye will see the tidal tails unwind. Whatever observes that sky, if anything does, will be something we cannot imagine, standing on a world that does not yet exist, around a star that has not yet been born. But that's not all, because two things in this story will not be scattered. They will find each other. The black holes. As the merger proceeds, the densest cores of both galaxies sink toward the center. Dynamical friction drags them inward relentlessly, and each core carries its own supermassive black hole, Sagittarius A star, with about 4.3 million solar masses, and Andromedas, with perhaps 100 million or more. Over hundreds of millions of years, they spiral closer, until they are bound to each other in a binary orbit. Two dark giants circling in the crowded heart of a newborn galaxy. Each passing star that comes too close is flung away, and every ejected star steals a little orbital energy, tightening the pair. Eventually, the light years become light months, then light days. As they close, they begin to stir the fabric of space itself, radiating gravitational waves, ripples in space-time, carrying energy away at the speed of light. The final act takes only minutes. The two black holes whirl around each other hundreds of times per second, their event horizons nearly touching, and then merge into a single object. In that instant, an amount of energy equivalent to several million suns is released, but not as light, not as heat, purely as a shudder in the geometry of the universe, spreading outward forever. It would be the loudest event in this corner of the cosmos, and completely silent. Nothing would flash, nothing would burn. Space itself would simply ring like a struck bell, and then settle. Now, let's look at what is finally left behind. A single enormous galaxy, roughly spherical or slightly egg-shaped. No spiral arms, no dust lanes, no flat rotating disk. Just a vast, smooth swarm of stars, orbiting in every direction at once, densest at the center and fading gradually outward into the dark. Its color will change over time. During the starburst, it blazes blue with hot young stars. But that burst consumes the galaxy's gas at an enormous rate, and the supernovae and the newly awakened central black hole drive much of what remains out into intergalactic space. Once the gas is gone, star formation stops, and a galaxy that has stopped making stars slowly changes color. The brilliant blue giants live only a few million years and die. The white and yellow stars follow over billions. What remains in the end are the small, patient, long-lived red dwarfs. Trillions of them, burning slowly and steadily for hundreds of billions of years. Astronomers have a phrase for galaxies in this state: red and dead. It sounds harsh, but it describes something peaceful, not violence, stillness. A galaxy that is finished building and is now simply keeping what it made. Milkomeda will glow with a soft, warm, reddish light. Quiet, enormous, finished. Two great spirals, each billions of years in the making, reduced and combined into one calm ellipsoid, drifting in an otherwise empty sky. But what happens when we look for evidence that any of this is true? We look outward, because the universe has already performed this experiment countless times and left the results hanging in the sky for us to study. About 65 million light-years away sit the antennae galaxies, two spirals caught partway through a collision that began several 100 million years ago. Their cores are still distinct, but two enormous curving tidal tails sweep outward from them like insect antennae. Between the cores, the gas has ignited into one of the most intense starbursts we can observe. Thousands of brilliant young star clusters blowing along the collision front. Farther out, the mice galaxies show us a slightly earlier stage. Two spirals, still recognizable,
each trailing a long, straight, luminous tail of stars torn free by the first pass. Then there is Stephan's quintet, a tangled group of galaxies locked in an ongoing gravitational argument where one member is currently plunging through the group at high speed, driving an enormous shock wave through the intergalactic gas. And everywhere in the universe, especially in the crowded centers of galaxy clusters, we find the finished product. Giant elliptical galaxies, smooth, featureless, red, and enormous, each one the settled remnant of mergers that ended long ago. We are not guessing about our future, astronaut. We are reading it in the sky, written in the lives of other galaxies at every stage of the same slow story. And yet, there's more to this story, because the ending is not as certain as it once seemed. For years, the collision was described as inevitable. Textbooks stated it plainly. 4 billion years, head-on, no escape. Then the measurements improved. The Gaia spacecraft mapped the motions of stars with a precision no earlier instrument could match, and revised Andromeda's sideways drift. Astronomers also began to appreciate how much the rest of the local group matters. Andromeda and the Milky Way are not two isolated points falling through empty space. The large Magellanic Cloud tugs on us. Triangulum tugs on Andromeda. Their masses are uncertain by tens of percent, and small uncertainties extended across billions of years grow into very large ones. When researchers ran many thousands of simulations, varying each uncertain quantity within its measured error range, the results spread out. In a large fraction of those runs, the galaxies merge as expected.
In many others, they pass by each other, separate, and do not settle for far longer. Perhaps not within the next 10 billion years at all. Some recent analyses put the probability of a merger within 10 billion years at close to a coin flip. This is not a failure of science. It is science working exactly as it should. A prediction stated with false confidence has been replaced by an honest one. The most likely future still ends with two galaxies becoming one. But the universe has not finished telling us when or whether, and there is something calming in that uncertainty. Not everything is settled, not even the sky. The journey continues, one last time, into the deep future. Assume the merger happens. Assume Milkomeda forms and settles into its quiet red glow. What does its sky look like tens of billions of years from now? Almost empty. Dark energy will still be stretching space, and the expansion is accelerating. Every galaxy outside the local group is being carried away from us faster and faster. Their light stretches toward longer and longer wavelengths, dimming, reddening, and eventually fading below any possible detection. One by one, the distant galaxies will slip past the cosmic horizon. Not because they fall in, but because the space between us grows faster than their light can cross it. In perhaps 100 billion years, Milkomeda will be alone. A single island of stars surrounded by absolute blackness in every direction. Any astronomer born into that era would look up, measure carefully, and conclude that their galaxy is the entire universe. There would be nothing else to see. No other galaxies,
no evidence of expansion, no trace of the Big Bang left in the sky. The truth would still exist, but the evidence would be gone, which makes this moment we happen to occupy remarkably fortunate. We live early enough to still see the universe as it is, galaxies scattered to the horizon,
Ancient light still arriving, a cosmos wide open and readable for anyone patient enough to look up. Take a quiet moment to reflect on what this means, astronaut. Everything you have heard tonight is a story about something being lost. The Milky Way will not survive. Its spiral arms will unwind. The soft band of light our ancestors saw arching over every night sky in human history will be pulled apart and scattered. The constellations are already dissolving, slowly, star by star. And yet, nothing is truly destroyed. Not one atom is lost in the merger. Every star that shines tonight will still be shining. The carbon and iron and oxygen made in ancient stellar cores will still be here, folded into new clouds, gathered into new suns, perhaps assembled into new worlds and new eyes looking up at that unfamiliar sky. What ends is the arrangement, the shape, the particular pattern of things. And perhaps that is the gentlest lesson the universe offers. Nothing permanent was ever promised. Not to galaxies, not to stars, not to us. What we are given instead is a turn, a span of time in which to exist, to notice, and to understand. Somewhere out there tonight, 2.5 million light years away, 1 trillion stars are falling slowly toward you. They have been falling since before your species existed. They will still be falling long after the last human memory has faded. And you got to know about it. That is not a small thing. We turn back now and let Andromeda drift behind us, still falling, still patient, still 4 billion years away from an embrace that has already begun. Below us, the Milky Way turns as it always has, its arms still curved, its center still glowing. Everything still in its familiar place, for now. There is no urgency in any of this. Nothing you must do, nothing that will change before morning. The galaxies will keep their appointment whether anyone watches or not. And the sky above your roof tonight looks exactly as it did last night, and as it will tomorrow. Close your eyes now. Let your body grow heavy. Let the enormous, unhurried patience of the universe settle over you like a blanket. 4 billion years is a long time. You can rest. Mission complete, astronaut. The stars will wait for you. Good night.